Okay, so we talked about 2D transformation last week, right? We talked about what is the translation and what is the rotation and how it is done in processing. And for the convenience of drawing shapes on a coordinate system, processing handled this by transforming the coordinate system instead of the shape or the pixels itself. Okay, all of these are really just relatively speaking, whether you're transforming the shape or whether you're transforming the coordinates, they all eventually has the same effect visually. Okay, today we're going to talk about a more generic form of the transformation matrix that allows you not only to do translation, rotation, but it will also allow you to do shearing, mirroring, scaling, and a whole bunch of stuff. Okay, and this is a more generic forms that handles any kind of 2D transformations. And this is more mathematical way, but it is really the way to do transformation. And it just in processing implemented the functions to do all of these behind your back. But today we're going to see how really in mathematical everything gets computed. Okay. All right. So we're going to do that in OpenCV. If you not familiar with what OpenCV is, we did use it to introduce image and what image is composed of digitally, what they looks like. They just look like a grid of numbers, right? So we use that. We used OpenCV for that. And today we're gonna use OpenCV for the transformation of matrix of image as well. So OpenCV really it is the library, the Python library for anything related to machine vision. Okay, whether you want to use machine vision to detect people, to detect face, to track objects, and to do all sort of fascinating things, OpenCV is the library to use, and it is very widely used in the industrial when they do machine vision stuff. Okay, so this is a very large and complicated library to play with, but it is at the same time very interesting. All right. So I'm going to skip this section. We're just doing the necessary importing and reading the image in. So you can see I provided an image that we can see that this image is not straight, right? It is at an angle and is tilted and all that. So let's see if we can try to make it straight. We see that in many of the apps on your phone that they have this sort of features, right? When you it's what digital scan use, right? When you take your phone and take an image, even though it is tilted at an angle or something like that, the digital scan software can detect it and realign it back to a square, a right angle image, right? So we're gonna try something today and see if we can make that happen using the transformation matrix, okay? Okay, so first of all, read the image in cv.imread, and we're gonna read the image in as a grayscale because it is simpler. We don't have the 3 dimensions of colors to deal with. We just have a 2-dimension number grid for the black and white image. Okay. Okay. After that, we can start to do some transformation. Okay. Can anybody tell me does anybody look at, saw this sort of form, this sort of math before?
Didn't we like see that last time for like I think it was like rotation?
Yes, rotation matrix, I show you guys. It is this kind of forms. Did you see that in school yet?
No, I'm still way too young.
Okay.
No.
How about Eva? Did you see that in school?
This?
Yeah, like this form of
No.
math. Okay. So
I've
okay,
never seen.
let's explain it a little bit. It is nothing to be intimidated about. It is really just a cleaner way of writing multiple formulas together. We can say this way. Okay, when so these are called matrix, okay? You can all of these, like 1 matrix, 2 matrix, and 3 matrix. You can call this one is a 1 by 3 matrix. And then this one is a 3 by 3 matrix. And then this one is a 1 by 3 matrix, right? Okay, and then what really this means is that it is actually shrinking 3 formulas together into a cleaner visualized form. So I'm going to write down here what this matrix multiplication represents. What it really represents is that it is saying x pi equals to, so what we are doing here is we are taking the first row and then this guy over here and multiply them 1 by 1. Okay, so this guy multiply the x, this guy multiply the y, and this guy multiply this, and then add them together. Okay, that's what this kind of writing means. So what we are having here is actually 1 multiplied by x plus 0 multiplied by y plus bx multiplied by 1. Okay, so that finished the first x pi, and then same thing for the y pi's. So y pi, how is it calculated? It is by this row multiplied by this columns and then add them together. Okay, so y pi just means that y pi equals to 0 multiplied by x plus 1 multiplied by y, and then plus by multiplied by 1. All right. And then the last row is same thing. So we're taking the third row. This guy is at the third row. So we're taking the third row and then multiply this columns and then add them together. And here we have 1 equals to 0 multiplied by x plus 0 multiplied by y plus 1 multiplied by 1. So that is 1 equals to 1 on both sides. Okay. Oh, it doesn't come out very nice. Let me fix this up. So this is LaTeX syntax. All right. Oops. As you can see, this is really just a compact way of writing 3 equations together, right? And then we can see on this section here, what we are doing here is really 0 multiplied by y is 0, right? So then what we have is x pi equals to x plus bx. So that is a translation, right? You're basically moving every pixel at x by adding a bx to it, and that is the new coordinate for that pixel. So that is a translation. Same thing for here. So the 0 multiplied by x is 0. Then what we ended up is y plus by, right? So that is a translation on y-axis. And this one, that's 0, that's 0. And you have both sides, just 1 equals to 1. So this one doesn't have any meaning. We don't need to care about that. But this way of writing matrix, you will find that this single 3x3 matrix can represent many transformations, including rotations, scaling, shearing, and many kind of transformation can all fit in this little 3x3 matrices. So that gives people a generic way, a common way to represent the mathematics in a 3x3 grid of numbers. Okay, so that is the advantage or the motivation of representing these things in matrices, because they are very generic forms and they can be used in many kinds of transformation. Okay, any questions so far?
No.
Okay, how about Eva and Sandy? Can you guys follow?
Yeah.
Okay, good. All right, so as long as you can follow what I'm saying, that's good enough, okay? We don't ask you to do this kind of from here, go to here for now. We don't need to do that. Computer does all of the jobs for you, okay? We just need to know what this is. This is called the transformation matrix. And you can see that when we define a translation, we put the translation numbers as certain locations. You cannot put them anywhere you want, because other positions are for other things. When we define translation, they have to be put at the third column, at the first row and second row. Okay, they have their fixed location. So that's what we need to pay attention. All right, so let's look at an example. I need to first run these cells to load the image. All right, so, okay, so now here we define a translation matrix. Okay, so BM, because my translation matrix is defined as the number is defined by BX and BY. So I define this variable as BM, M for the matrix. So this is a NumPy way of defining matrix. Basically, you can visualize this even when you write this. So we can see that this is a 3x3 matrix, right? So the BX we are defining here is 500, and the BY is also 500. And at the end, I print it out and it looks like this, okay? That's our translation matrix. And how to apply this? So say if you want to transform your image, then so this is the function in OpenCV that we use to transform a image. The way to use that is you first supply the image, okay? And then you supply the matrix. And then you also need to tell OpenCV what's the size of your matrix. And then you get the result out of this function, and you assigned it to another variable. After that, you can show this new image, what it looks like. All right. Okay, and let's run this. Okay, I haven't run this. All right, so you can see the result. what happens here is that we translate this image by shifting it to 500 and 500 on X and Y axes. Okay, so that's translation. Very easy. Okay, let's move on. Next, rotation matrix. That's what we showed last class. Okay, so what we showed last class is this 2x2 matrix, right? As you can see, that this 2x2 matrix, when it sits into a more generic formula, they sit in this location, right? The first row and then first two columns. Okay, and the theta represent the amount of rotation that you want to apply to the image. So I'm gonna go quicker now, because they are all in the same matrix. Same thing, you defined your matrix. Here, we need to pay attention that the all of these angle functions, you need to give it a radius. Okay, Sandy, know what's a radius? Radians?
Yeah.
Yeah?
Yeah. Well, I kind of forgot, but yeah.
A circle is 360 degrees, right?
Oh yeah. Yeah.
360 degrees, but it's in radians, it is also 2 pi. 2 pi. Right? So 2 pi is the radian. That's just different different unit for describing an angle. So 360 is the degree. The unit is degree, but the 2 pi is also a full rotation of a circle, but this 2 pi, the unit is radian. Okay, they describe the same thing, but they have different units.
Oh yeah.
So
Okay.
how do you convert a degree to radian? Is basically, say I have a if I have a degree, an angle that is 45, then how do I convert that? Basically, I have to take, first of all, take 360, divide by 2 pi. That's the easiest way to remember. So that basically gives you how many degrees per radian, right? So this unit is degree per radian. I think it looks like that, per radian. And then you take this, you multiply by 45, or the angle that you want to do. So that gives you what is 45 in radian. Okay?
Okay.
It's like a fraction. So it's like 45 is how many fraction of the 360. Then you just take the same fraction and then of the radian and then take the same portion. That's the idea. Okay.
Yeah.
Okay. So we just need to pay attention that this has to be a radian and not an angle. Okay. Not the degree, has to be the radian, and you need to convert that. Okay. All right. So and then we construct the matrix following the formula, put them in the right place, right? And then you get a rotation matrix. And now we just apply the same way, right? Take the image, provide the matrix, rotation matrix, and then provide the size of the image, and then blah. Dum. Oops, I haven't run this yet. And run this. Okay, there we go. So I just rotated my image by 45 degrees. All right, so far so good. Once you get to the code part of the thing, everything is very easy, right?
What does theta mean?
Huh?
Theta or
Theta. Well, theta
theta.
is a Greek symbol. When you Usually in math, we use the Greek symbol to represent angle. Whenever you have an angle, people like to use the Greek symbol. Yeah, theta is this. Does it ring a bell? Have you seen this before? There's also alpha, that's alpha. And there's beta. That's very often used when we name an angle. When we give a name angle a name, that's usually what we use, and theta. Okay. All right, so let's move on. Next thing, scaling. Okay, scaling, you can see same matrix, just different locations, right? So the scaling on the x-axis, this scaling factor is at the location of 1, 1, and then this one for the y-axis, it sits on 2, 2, okay? And then you just define the matrix again. Let's run this, and you got a scaling matrix, okay? And apply this to the image, and you shrink it by half. Okay, so you see this is the proportional change for the scaling. If you want to change it to 0.2, then that will be even smaller. So we're shrinking x more, and it looks like that. All right, the scaling. And shearing is basically moving things into a parallel, how do you call that? Parallelogram kind of change. It basically, say if you have a square, if you have a shape like this, then shearing just means that you change it into a shape that looks like this. Okay, that's what it looks like. So this is the x-axis of shearing. And there's also the y-axis of shearing, which is I can't twist my brain around this either. That it will look like that. That will be the y-axis of shearing. Okay, so this is the x, and this is the y. It looks like this, and we can check it by just play with our matrix. So let's define on the axis, on the x-axis, I want to shear by 0.5, and on the y-axis, I don't want to shear, so I give it a 0. Okay, so that's my transformation matrix, and let's apply the change. Yeah, so this is shearing on x. Except I draw that shape upside down. Can you guys see can you make sense of the change here?
Yeah.
Okay, good.
I have a question. Will we like be able to get like the Google Colab? It's like it's kind of hard. It will be hard to code like without it.
Yes, you can code it in Google Colab. It's convenient to code because Colab has the CV, and you don't have to install.
I mean, like, can we have like the link to this collab?
You want the link to my notebook?
Yeah.
Okay. Yeah. It's just in Python 3. In here, Python 3, and then you will see that. The image is also here. You can download it.
Okay.
The name is Transformation in Machine Vision. You guys all have access to this. Okay, let's try the on the y-axis, what's gonna happen. So if you don't want to shear on x, then you just set it to 0. And then for this one here, we can write the matrix this way, okay? When you see a comma, you can start a new line, and that's not going to affect your matrix definition. This way you can better pinpoint which number you're supposed to change. So if I want to shear on y, let's do a smaller change and then apply. apply to the image. Okay, so you can see that we're shifting. So on the Y, I draw the right thing. So it's doing this. Okay, so all of these parts has been moved. Any questions? Are you okay, Sandy, Eva?
Yeah.
Okay.
Yes.
Huh? Okay, so next thing, the mirroring. Okay, X mirroring and Y mirroring. So if we compare, so this is the matrix for doing the X mirroring and Y mirroring. That's the X and that's the Y. If you look at this, you can kind of see that, remember, this is the translation number go to, right? The translation number go to here. And so is this. So that's translation. And this spot is the rotation matrix. That's where the rotation matrix goes to, right? So that's the R matrix. So we can see that the mirroring is actually accomplished by a combination of translation and rotation. So if you think about it, it kind of makes sense. It's kind of like, say, if you have an image. So at first I will move it. I'll move it here. And then I rotate it by 180 degrees. And that is the what? X. So it's mirrored by X, by this axis, right? So the mirroring is done by a combination of rotation and translation. Okay, so now let's try this. First, mirroring by X. And there, our image is upside down. So you guys can change this matrix. Oh, so here's what I did for Y-axis. I already done that. I was trying to get you to do it. Okay. Okay, so all of these are simple. You just need to know that when you define the matrix, where you want to change the number. So the place where you want to change the number, you just look at this form, and it tells you which number you should change to bring what kind of effect. Okay. Okay, so now next, we need to specifically talk about this, the order of transformation sequence. The transformation, when you swap the order around, it does not bring the same effect. Okay, and this order here, do translation first, and then scaling second, and then shearing third, and then rotation fourth, and reflection last, is the order where people can intuitively think and see things happening. And it's going to come out as you predict, as your brain predicts. Okay, if you don't do it in this order, your brain can't really figure out what is going on. It's like when you do the rotation first, and then if you do the translation second, then the thing is not going to be appear as translated, or it's going to be translated into a totally different location, not by the number that you originally wanted. Okay, so that's something we need to pay attention. Now, if we want to restore this image, so this book, if you want to restore it into you know, as if you're looking at it from straight down into a perfect rectangle, then you have to do a combined of shearing and translating and rotation. So you need to do a combine of these things. And you want to make sure that you do this in these orders. Otherwise, things will be very unpredictable. Okay, so how do we apply multiple transformation? You can always do this step by step, like when you define your translation matrix, and then you apply it to the image, you get a result. And then you apply the second transformation on the result to get the third result, and so on. You can do this. Or we can use matrix multiplication to combine the matrix and then do the transformation at one shot. So I'm gonna demonstrate one example here. Okay, here, so I have a combined translation matrix. Okay, so this is a translation, and then another rotation matrix. Okay, so I have two matrices. Actually, I have three. I'm just going to take this one out for now to make it simple. So how do you combine matrix? In matrix multiplication, this is called a dot product. You don't have to be too afraid of these new terms. It's just the way, the rules of multiplying matrix. Okay, they are called a dot product. And so NumPy provides you with the function to do exactly that. So we just need to know what to call it and where to put stuff in. So to do a matrix multiplication, you just need to tell NumPy, okay, so here's my result that where you want to dump the resulting matrix into, right? And call NumPy dot. And then you put the first matrix in, and then the second matrix. And that's how you combine these two matrices. Okay. So after you do that, let's take a look at the matrix. So M, print it out. Okay, there you go. So we can see that the matrix get combined properly. We want to translate 50 to 50, so it does that, right? And we want our rotation, so it does that. And then all of the other position that we are not using, they are the set proper value. They're 0, 0, and 1. Okay, so what happens if I don't do it in this order? Let me just show you an example. If I don't do it in this order, I do the rotation first and then translation. So I do rotation first and then translation. And let's show what the M looks like. Okay, there. So you see our rotation, our translation is no longer 50 and 50 is off. It's off by a odd number that's kind of unpredictable, right? So that's why we need to strictly follow the order of sequence when you do multiple transformation. Okay, all right, and so now let me put back my correct matrix. And now I can do the combined transformation on my image by just using this last matrix, my end result matrix, and apply it. And there you go. That's my end result for my for transforming my image. All right. So this is how you use the transformation matrix and how you create a matrix and how you use the matrix to manipulate the image into a different perspective. So now my challenge to you is that so at the end of this notebook, I gave you 3 matrices, right? I think these 3 combined together should do it. And I even give you the correct order. So this is the correct order. Okay, so you do the translation first and then oh, sorry, no. So we should do translation first and then shearing and then rotation. So we should do this. And then RM at the end. So we should do it in this order. So can you actually transform this image so you get a rectangle, a right rectangle book in the end? So try, let's spend 15 minutes to play with this. Okay, you don't have to get to the end, like get to a perfect result, but just spend 15 minutes to play with these matrix and see what you come out of it. Okay, and then we'll go back to everybody's individual work. Any questions? You guys can get this notebook in the in my Google Drive, Python 3. Just go into this Drive folder, and then transformations in machine vision. So once you open that notebook, make a copy into your own Google Drive. All right. And the image that I'm using is also in the same location. It is this one here, IMG 2421. And remember that you have to upload. So download that image into your own computer and then upload it into this workspace before you can load this image. Any questions?
Wait, where do you find the the notebook again?
In the Python 3 folder.